Einstein's theory of general relativity has passed the most rigorous test to date. When Albert Einstein started developing his new theory of gravity, Max Planck told him, "In the first place, you won't succeed, and even if you do, no one would believe you." But Einstein was so determined, he spent a decade developing his general theory of relativity. The first evidence supporting general relativity came in 1919, when English astronomer Arthur Eddington confirmed the predicted deflection of starlight by the sun during a total solar eclipse. Over the past century, Einstein's relativity has been tested several times to check its accuracy, and each time it has held a firm stance. And now, once again, a core principle of Einstein's relativity has passed the most rigorous test to date. So what is this test about? Which core principles of relativity did this test target? Finally, and most importantly, how does it solidify our modern understanding of gravity? One of the most important principles of Einstein's general relativity is the equivalence principle. It says that all objects, regardless of their mass and composition, would accelerate in the same manner in the same gravitational field when no external forces act upon them. Confused? Let me put it in simple words. Suppose you simultaneously drop a feather and a stone towards the ground from the same height in a perfectly resistance-less environment. Which one, according to you, will touch the ground first? One may think that as a stone is more massive than a fragile feather, it should experience more gravitational force and hit the ground first. But that's not the case, because as per the principle of equivalence, both objects should fall simultaneously on the ground. In other words, one can say that the inertial and gravitational mass of a body is proportional to each other, which makes the acceleration independent of the physical nature of the body. Now, what is the difference between inertial mass and gravitational mass? The mass that appears in Newton's second law of motion is termed inertial mass. It simply describes how difficult it is to accelerate an object. On the other hand, the mass that appears in Newton's universal law of gravitation is the gravitational mass. It depicts the strength with which gravity acts on a body. So although a stone has more gravitational mass than a feather, the force of gravity acting on it is greater. At the same time, its inertial mass is also greater, which makes it difficult to accelerate. So the two effects cancel out, and it falls with the same acceleration as that of the feather, which is precisely the value of acceleration due to gravity in free fall. No matter how small, if there's any violation in the proportionality between inertial and gravitational mass, Einstein's entire system breaks down. This makes it extremely important to look for such violations experimentally. In 1971, during the Apollo 15 mission, astronaut Dave Scott became the first person to demonstrate this effect. While standing on the moon, he simultaneously dropped a hammer and a feather from the same height. There was no air resistance to slow the feather, so the two objects dropped to the moon's surface at the same speed. This experiment was inspired by Galileo's experiment from the 16th century, where he dropped two different balls from the top of the Leaning Tower of Pisa to find them reach the bottom at the same time. Although Galileo's experiments were accurate to only about 1%, the accuracy and precision have improved by several orders of magnitude over the centuries. And the accuracy of the current experiment that we will discuss has broken all the previous records. This experiment is called microscope, headed by late physicist Pierre Touboul. It involved a satellite that circled over Earth in orbit from April 25, 2016, until it was deactivated on October 18, 2018. During these 18 months, multiple experiments were conducted using different masses suspended in free fall. This resulted in a total of 5 months of data, where 2/3 of the data involved pairs of test masses of different compositions, which were alloys of titanium and platinum. The remaining third part involved a reference pair of masses of the same platinum composition. The team used electrostatic forces to keep the two test masses in the same position relative to each other. Further, if there appeared any difference in the acceleration of the two masses, it was reflected precisely by the system in terms of changes in the electrostatic forces holding the masses in place. In technical terms, this difference in acceleration is known as the Iot-Voss ratio. These results were initially released in 2017 and were quite promising. They found no violation of the weak equivalence principle down to an Iot-Voss parameter of -1 plus or -9 into 10 raised by power -15, which is very impressive. However, the satellite was still operational, which meant the work was incomplete, and there was still room for improvement. And now the findings are clearer as the full data set is available. The experiment has found no violation of the principle, constraining the Iot-Voss parameter to 1.1 parts in 10 raised to the power of -15. This is the tightest bound placed on the weak equivalence principle to date and is unlikely to be exceeded soon. This means that the weak equivalence principle has held itself firmly, and we can safely continue to rely on general relativity with even more confidence than ever. However, general relativity breaks down on atomic and subatomic scales, and quantum mechanics takes over. Following this, scientists have been trying to resolve the differences between the two for quite some time. Also, the weak equivalence principle isn't the only inference of Einstein's relativity that has been put through vigorous tests. Many other ideas associated with general relativity are being tested regularly. For instance, one of the significant conclusions of general relativity is that gravity impacts the behavior of space-time. It says that massive objects curb the fabric of space-time around them to a greater extent than less massive objects. This means that around highly massive and dense bodies like neutron stars, the light will get visibly bent as photons will have to follow the warped path of space-time. Further, when neutron stars accelerate while spiraling around one another, they will send out ripples in the fabric of space-time that will travel as gravitational waves. The loss of energy with time will cause their orbits to shrink. Although gravitational waves have already been detected in 2015 by LIGO, a team of researchers observed both of these theoretical predictions simultaneously on 2 pulsars in December last year. They used 7 radio telescopes in Australia, the United States, and Europe to monitor a double pulsar system between 2003 to 2019. The companions were found to orbit each other in just 147 minutes at speeds of up to 1 million kilometers per hour. While one of the pulsars rotates around its axis about 44 times every second, the other rotates once every 2.8 seconds. And every time a pulsar rotated, the telescopes received a blast of radio pulses on Earth. However, the pulses were recorded to consistently arrive later than expected. Studies revealed that this delay resulted from the pulses deflected at an angle of 0.04 degrees due to the strong space-time curvature around the two stars. This observation marked the first ever experimental evidence of such a high curvature around neutron stars. Furthermore, the group found that the orbit of the pulsars witnesses a shrinkage due to the emission of gravitational waves. This test detected the energy carried by the gravitational waves with precision around 1,000 times better than that possible with direct gravitational wave detectors like LIGO. At present, Einstein's relativity is the best theory we have of gravity. However, as we said earlier, it breaks down at atomic and subatomic scales, and quantum mechanics takes over. So general relativity is not the holy grail of physics. Nevertheless, experiments and studies like this will help us advance a step forward to a concrete unified theory of gravity. This concludes the 30th episode of the Sunday Discovery series. So, if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any further videos of this series.